Today we will start with aldehydes and ketones. In this we will do first preparation from 1,3-diethane, then the mechanisms involved in nucleophilic addition reactions, that is in which small molecules are removed, and the second in which small molecules are not eliminated while the nucleophilic addition reactions. So first is preparation from 1,3-diethane. 1,3-diethane is prepared from the formaldehyde with this 1,3-propane dithiol in the acidic medium, that is to give 1,3-diethane and water. So 1,3-diethane is prepared from formaldehyde and 1,3-propane dithiol. It is propane, there are 3 carbons, and then OH groups are replaced with SH, that is oxygen is replaced with S, therefore thio is used. There are 2 OH groups, 2 SH groups, so it is dithiol. So when formaldehyde reacts with 1,3-propane dithiol in acidic medium, that is in the presence of trace of acid, then we get 1,3-diethane, which is very important for the preparation of aldehydes and ketones. So we are concerned mainly with 1,3-diethane, how we can prepare aldehydes and ketones from this 1,3-diethane. That is, first we will take up the preparation of aldehydes from 1,3-diethane and then the preparation of ketones. So first is 1,3-diethane is treated with butyl lithium in the presence of tetrahydrofurane. Then butane is removed and we get this lithium abstracts the proton, that is this proton is combined with butane, we get BUH, butane, and here the negative charge because the hydrogen has been abstracted. So electron pair with negative charge and lithium is associated here. Now this negative charge is present, so this acts as a strong nucleophile, and these nucleophile then reacts with alkyl halide, in which through this electron pair it forms bond with alkyl group, and this halide is removed and it combines with lithium as lithium halide. So this alkyl group now joins with this carbon, this is formed, and then this upon treatment with HgCl2, methyl alcohol, water, that is one type of hydrolysis, then it gives aldehydes and this open chain, that is 1,3-propane diethane. Diethane is formed as a product. So synthesis of aldehydes can be done by this 1,3-diethane with normal butyl lithium in the presence of solvent tetrahydrofurane to get this strong nucleophile, that is this carboanion, and this carboanion when treated with alkyl halide, then we get this alkylated product, and this alkyl, now here these upon hydrolysis these bonds break and here C double bond O is attached, C double bond O, and here the hydrogens get attached. So SH is formed, SH, and oxygen is attached here. So that is, it is a one type of addition of water in the presence of mercury chloride and methyl alcohol. So aldehydes are formed. And taking up a particular example, and this first step is same, that is with butyl lithium and tetrahydrofurane we get this carboanion, and in this we have taken our particular alkyl group. We want to prepare a particular aldehyde, so we have taken ethyl bromide. Now these ethyl halide, the ethyl group will get attached to the carbon, this carbon, through electron pair, that is this is attached to carbon, and now upon hydrolysis this bond will be broken, and here C double bond O will be attached, and to this hydrogen will be attached, so water is added across this, and we get C double bond O HCH2CH3, that is aldehyde of 3 carbons, 1, 2, 3. So it is a propanol, and the 1,3 propane diethane is formed, a dithiol is formed. So this is the way the aldehydes can be prepared from 1,3 diethane. This is important. It can be asked directly how aldehydes and ketones can be prepared from 1,3 diethane. So next is preparation of ketones from 1,3 diethane. This same, first it is treated with butyl lithium and tetrahydrofuran solvent, and then this carbon ion formed reacts with alkyl halide to give this alkylated product, and now this step is repeated again so that this hydrogen can also be replaced with alkyl group. So again with butyl lithium and tetrahydrofuran, then we get first carbon ion, and then with alkyl halide, and now this hydrogen is also replaced with alkyl group. So both the hydrogens present here are replaced with alkyl group. So upon hydrolysis, now here C double bond O will be attached, this C double bond O will be attached, 2 alkyl groups are present, so ketones are formed, and the other product is open chain, this, that is propane 1,3 diethol. So the step is same as for aldehydes, but here are these steps are repeated so that both the hydrogens get replaced with alkyl groups, and then hydrolysis is done. So taking up a particular example, and this first step is butyl lithium in the presence of tetrahydrofuran, and then the second step it is treated with this halogen, this alkyl halide, and here this group is present, and this will replace the hydrogen, and so here it is this. And in the second step, if it is repeated with butyl lithium and then this alkyl halide, and this alkyl halide will replace other hydrogen and this hydrogen, and we will get this. So 2 alkyl groups are present at this carbon, and now the hydrolysis will take place. When hydrolysis will take place, then this bond will break through these points, and here C double bond O will be attached. C double bond O, other groups are the same, and so it is a, here now it is a benzyl group, here it is a propyl group, so we get benzyl and propyl ketone. So it is the preparation of aldehydes and ketones. Now the next is nucleophilic addition reactions mechanisms. The reactions we have already done. The reactions involved in nucleophilic addition reactions, they are of 2 types, one in which elimination of molecules do not take place, and in the second elimination of small molecules takes place. So first is in which no small molecules are removed, that is reaction with HCN, then reaction with sodium bisulfite, then reaction with Grignard reagent, and then with alcohol in dry HCl gas. These reactions we have done already. In HCN, the products are called cyanohydrins. In this, bisulfite adduct is formed. In this, alcohols are formed, and in this, acetals, and then hemiacetals, then acetals, and or ketones and are formed. So the mechanism is the same because it is nucleophilic addition reaction. So in this first step, nucleophile attacks. So in HCN, the nucleophile will be CN negative. So CN negative attacks on the carbon, it attacks on the carbon, and now the electrons of this moves to oxygen, and CN gets attached to carbon, and O with O negative. O negative. Now with the addition of water, it abstracts hydrogen and we get OH and CN. So it is nucleoaddition reactions, that is nucleophile attacks the first aldehyde or ketone. So nucleophile is CN negative in this case. Similarly, in the second sodium bisulfite, we have NaSO3H, that is NaHSO3. So it is written as this. Now in this through these electrons it will attack this carbon when electrons will move towards oxygen. So, and this sodium gets attached to oxygen, that is ON is formed, and all other group, that is SO3H will be attached to this carbon, SO3H. So one OH group is present and it will be linked through single bond, other oxygen will be through double bonds. So now in this the proton transfer takes place, that is these are exchanged and we get this sodium bisulfite adduct. So when sodium bisulfite is reacted with aldehydes and ketones, then the sodium bisulfite is added across the double bond as ONA and SO3H, and then the proton transfer takes place. Na is replaced with hydrogen and Na comes to this, so it is OH SO3 Na, and so is and this product form is resonance stabilized. That is, we can say why the proton transfer takes place. This is the product. Then why the proton transfer takes place? This takes place due to because this product formed in which sodium and hydrogens are transferred, mutually exchanged, it resonance stabilized. It is resonance stabilized as, and this sulfur has three oxygens. When these electrons can move to this, here will be double bond, these electrons gets moved to this O with negative charge. So in this has negative charge, in the next this will have negative charge. Similarly, third oxygen can also have negative charge, so third has negative charge. So these are the resonance structures. So this is resonance stabilized, therefore in this proton transfer takes place. So next is the addition of Grignard reagent. In this has partial negative charge, so through this it forms bond with the carbon and these electron moves to oxygen, so MgX gets attached to OMgX and alkyl group to the carbon directly to these electron pair, and these are the strong nucleophiles. So now upon hydrolysis, this hydrolysis, that is addition of water and this in this these bonds breaks this like this. Now this hydrogen gets attached to O and OH groups attached to Mg, so we get COH R as such, and here the OH MgX, it is basic magnesium halide. So when aldehyde ketones are treated with Grignard reagent, then these attacks as such, first is nucleophile attacks to the carbon and other gets attached to oxygen in the presence of dry ether. Then the hydrolysis takes place in which OH and this is released, so we get a last alcohol, and this we have already done, that is formaldehyde gives primary alcohol, high aldehydes gives secondary alcohols, ketones give tertiary alcohols. And in this we have done one reaction, that is reformate-Keys reaction. What is reformate-Keys reaction? In this reaction we can say that is aldehydes and ketones react with esters. Which esters? That is alpha bromo esters. Alpha bromo ester means this is COOR group. This is COOR group, and this is alpha carbon. This is alpha carbon. To the alpha carbon, bromine is attached, so it is alpha bromo ester. When alpha bromo ester reacts with aldehydes or ketones in the presence of zinc and dry ether, we get this addition product in which zinc gets inserted between the halogen. Zinc gets inserted between the halogen, that is CH, Zn, Br, one type, and then this gets attached to this. When these electrons move to oxygen, and this bromine gets attached to the oxygen through zinc, OZnBr, OZnBr, and this carbon gets attached to this carbon. So this carbon gets attached to this carbon, because Br negative gets attached to the oxygen through the Zn, and we get this addition product. And this upon hydrolysis gives, this group is replaced with hydrogen, that is OH, so we get beta hydroxy. Now this is beta carbon because this is the ester group. Now this is alpha carbon and this is beta, so we get beta hydroxy ester as a final product upon the acidic hydrolysis. This reaction is called reformatic reaction. What is reformatic reaction? Is we can say reaction between aldehyde or ketone with bromoester in the presence of metallic zinc to give addition product which gives beta hydroxy ester upon acidification. This is called reformatic reaction. So this is the aldehyde or ketone with alpha bromoester in the presence of zinc and dry ether gives this addition product, and then upon hydrolysis gives the beta hydroxy ester. This is the final product. So taking a particular example, and this is acetone. Acetone reacts with this ester, this alpha bromoester in the zinc and dry ether, then we get this. Now this whole group will be attached to the carbon, leaving this bromine, and now OZnBr will be attached here, and this whole group to this carbon, and now this group is attached to this carbon, whole group, and then upon hydrolysis we get OH, that is instead of Zn, Br, hydrolysis takes place and we get OH, and remaining is the same. So this is the alpha carbon, this is the beta carbon, so we get beta hydroxy ester, and the name of this will be, in this we will start from here. It is the first carbon, then second carbon, then third carbon, then fourth carbon. It is fourth carbon. So the carbon chain is of 4 carbons. 4 carbons, so it is but. All are single bond between the carbon chain, so it is butane. Now if we see first, second, third, to the third carbon methyl is attached and OH is attached, and to the second carbon methyl is attached. So methyl group is attached to second and third carbons. So 2,3 dimethyl butane. Now third carbon also has a OH hydroxy group, so 3 hydroxy, and now here is it is COOR. In esters we write the alkyl group in the front, so this alkyl group will be written in the front as a prefix, so we get ethyl. Now out of OH group and methyl, which comes first in the alphabet? H comes first, so H will be written first. So ethyl 3-hydroxy 2,3-dimethyl butane. For a ester we use OH, butanoate. So it is ethyl 3-hydroxy 2,3-dimethyl butanoate. So this is the format key reaction. This can be asked in a naming reaction also. It is important. Now next is the mechanism for the reaction with alcohol in the presence of dry HCl gas. When aldehydes or ketones, that is we already know that aldehydes react with monohydric alcohols, but ketones react only with dihydric alcohols. So first is aldehydes. When aldehydes react with acid, that is dry HCl gas, then they form protonated aldehyde, and this is in equilibrium with this. This shows a resonating structure, that is if these electron moves to this, then we have this charge will be neutralized and carbon will have positive charge, thus, and this is in equilibrium with in the presence of alcohol, because we have done that dry HCl gas and alcohol. Then this alcohol group will be attached to this carbon carrying positive charge, this carbocation, and this group is attached to this. Now oxygen will carry positive charge, and then this hydrogen is released as H positive, and the electrons neutralize the oxygen, and we get OH, OR dash. This is hemiacetal, and this is unstable. So it is unstable, so it reacts with second molecule of HCl, and we get the same series of reactions. Then that is this will hydrogen will react with this to give water as released, and this will have positive charge, or this carbon will have positive charge, which is stabilized by these electrons, and this now oxygen carries positive charge, and then when the electron moves to this will have positive charge. Now a similar way as we have done here, this alcohol molecule combines with this carbon, that is carbon carrying positive charge. Similarly in this alcohol, that is other molecule of alcohol, gets attached to the carbon carrying positive charge through oxygen, and oxygen will have now positive charge, this, and then this hydrogen will release its electrons to this oxygen, and this will be neutralized, and we will get OR dash, and OR is also already attached, so it is a acetal. So the aldehydes and ketones react with alcohols in the presence of dry HCl gas to give the first hemiacetal. This is hemiacetal, but it is unstable, and it then with second if it is the reaction is repeated again, then this will go through these steps, and finally we get acetal. Now the reactions in which small molecules are eliminated, in this we have mainly done the addition of ammonia derivatives to the aldehydes and ketones, which are catalyzed by acids. We have done this is important, that is in the weakly acidic medium. In strong medium, the ammonia derivatives will have now nitrogen will have positive charge, they will no longer be the nucleophiles, so the medium should be weakly acidic. So in this aldehydes and ketones in acidic medium gives this, and which is resin stabilized. Now this carbocation combines with the ammonia derivatives, that is through the nitrogen, which carries electron pair. Through this nitrogen forms bond with carbon, and this is this nitrogen has two hydrogens and one group which can be varied. So this nitrogen has two hydrogens, one G group, and forms bond with this carbon, and now the carbon is has full octet. So now this nitrogen, because this forms bond with carbon, now this will have will become electron deficient, so it will have positive charge. So, and this is in dynamic equilibrium with this this one hydrogen will neutralize this nitrogen, and now this is neutral molecule, and then with H positive, this OH will form this protonated, and now here again this will be removed as a water by taking electrons of this, and this carbon will have now positive charge, which is compensated by the electron pair of nitrogen, and now nitrogen will have positive charge, that is this, and then this after releasing this electron, this hydrogen, and this electron comes to nitrogen, and nitrogen becomes neutral. So this product is formed, this additional product is formed with the elimination of small molecules of water, like here we have seen water is removed. So the addition of ammonia derivatives of any can be explained with this mechanism, in which we can replace H group by OH group, by NH2, by NHCO, NH3, by 2DNP. So the mechanism is same in all the ammonia derivatives, just this group will be changed. So in this, first with acidic medium, that is with H positive, this will get protonated, and then this carbocation is formed, and this on this carbocation ammonia derivative attacks as a nucleophile, therefore it is nucleophile addition reaction. So as a nucleophile, this attacks on this carbon, and this will be formed, and then after releasing H, this nitrogen will be neutralized, that is this, and then it will take up H positive, and this water will be removed, and now this carbon will have positive charge, but this is compensated by the electron pair from the nitrogen, and we get C double bond N, and now this positive charge is neutralized by the release of one H, and we get C double bond Ng. That is the last addition product with the elimination of small molecules like water in this reaction. So this is all about the mechanisms of the reactions of nucleophilic addition reactions, in which no molecules is removed or small molecules are removed. So next we will take up oxidations and reductions. Thank you.